Welcome back to The Explainer. Today, we are exploring something that literally shapes our entire world, yet it's completely invisible. I'm talking about heat. Whether you're stepping into the warm sunshine or sipping a hot cup of coffee, you feel it every single day. So in this Explainer, we're going to dive right into a comprehensive overview of Chapter 9 from the KSSM Science Form 2 curriculum. We're going to uncover the fundamental science and those microscopic actions that drive some truly massive everyday consequences. Here is our roadmap for today. We'll start by comparing heat versus temperature, then look at how heat flows, and explore reaching thermal equilibrium. After that, we'll examine expansion and contraction, and wrap the whole thing up with heat absorption and emission. Section 1. Heat versus temperature. You know, in our everyday lives, we tend to throw around the words heat and temperature like they mean the exact same thing. But in physics, they are entirely different. To get us in the right headspace here, I want you to ask yourself something. Why exactly does a frozen treat melt on a warm day? Like, what are the invisible forces actually doing to turn that solid ice into a puddle? The answer is actively happening right in front of us. When a frozen treat melts, it isn't just passively getting warm. Heat, which is a literal form of energy, is actively flowing directly from the hotter surrounding room right into the colder object. It's a fundamental rule of the universe. Heat always travels from a hotter region to a colder region. So, that brings us to the core difference. Heat is a form of energy. It can actually do work, and we measure it in joules. Temperature, on the other hand, is really just a measurement. It's the degree of hotness or coldness based on particle movement, and we measure it in Celsius or Kelvin. Temperature can't actually do work, it just tells you the state of an object. Plus, the total amount of heat in something, that depends on the type of material, its quantity, and its temperature, all working together. Section 2. How heat flows. If you think about a pot of water boiling on a stove, you're actually witnessing 3 completely distinct methods of heat transfer happening all at the exact same time. It's pretty cool. Energy moves through the solid handle, it circulates through the liquid water inside the pot, and it radiates through the open air moving away from the burner. Let's break those 3 down. First up is conduction, which happens in solid mediums. Imagine this unseen world of particles gaining energy and colliding into each other, literally passing the heat right down the chain. Next is convection. This happens in fluids, so that means liquids and gases. What happens here is the heated fluid actually expands, becomes less dense, and then rises to create a continuous circulating current. And finally, radiation. Now this one transfers heat without any medium at all. It moves in electromagnetic waves straight through a total vacuum. To really ground that last kind of abstract concept in a massive natural phenomenon, just think about our own planet. The sun warms the Earth entirely through radiation. That immense heat energy travels through the absolute vacuum of space, without any solid, liquid, or gas medium to carry it along the way. It arrives here at the exact speed of light to sustain all life on our planet. When you think about it, it is a completely mind-blowing scale of heat transfer. Section 3. Reaching thermal equilibrium. Now, heat doesn't just flow aimlessly out there. It actually has a destination in mind. Thermal equilibrium is the state where 2 objects that are in contact finally reach the exact same temperature. That relentless, unstoppable flow from hot to cold continues until both objects are perfectly balanced. And once that happens, boom, there is zero net heat transfer between them. Section 4. Expansion and contraction. So what actually happens to matter when it absorbs all this energy? Let's paint a little microscopic picture here. Step 1, matter is heated. Step 2, its particles absorb that energy and start vibrating or moving a lot faster. Step 3, because they're moving so rapidly, the actual physical distance between those particles increases. And finally, step 4, this increased distance across millions and millions of particles expands the overall volume of the object. We call this expansion. And conversely, cooling things down slows the particles, bringing them closer together, which results in contraction. Now, you might be wondering, okay, why does this matter to me? Well, engineers have to account for this invisible particle physics every single day. Thermometers rely completely on a liquid expanding uniformly as it absorbs heat. Railway tracks are deliberately built with small gaps left between the rails, otherwise they'd warp. Massive steel bridges, They're built with rollers and gaps at one end so the bridge actually has room to physically grow on a hot day. Even fire alarms use bimetallic strips, like iron and copper, that expand at different rates when exposed to heat, bending to complete a circuit and trigger the alarm. To make this concept stick with you, just consider the sheer, unstoppable physical force of thermal expansion. We aren't just talking about a microscopic shift here. Without those small expansion gaps we just mentioned, solid steel railway tracks weighing thousands of pounds would literally bend, buckle, and overlap under the immense pressure of summer heat. That is just how incredibly powerful the invisible energy of heat truly is. Section 5. Heat absorption and emission. So, how does the outer surface of an object actually dictate its relationship with heat? Well, it mostly comes down to color and texture. Dark and dull surfaces are excellent heat absorbers and excellent radiators. They take in and release heat super rapidly. Conversely, white and shiny surfaces are poor absorbers and poor radiators. They actually reflect heat. This is exactly why a black car gets so incredibly hot sitting in the sun compared to a white car. The dark surface actively absorbs the sun's radiant heat, while the white surface bounces it away. And here's a brilliant real-world industrial application of this exact concept that you'll probably see the next time you're driving on the highway. Large fuel tanks, especially the ones transporting highly flammable liquids, are almost always painted in bright, shiny, reflective colors like white or silver. Because those shiny surfaces act as poor heat absorbers, they reflect the radiant heat from the sun. This keeps the inside of the tank cooler and dramatically decreases the dangerous evaporation and pressure buildup of the fuel inside. Pretty smart, right? So we've explored the core difference between heat and temperature, how heat flows, the physics of expansion, and the power of surface colors. To conclude our explainer today, I want to leave you with a very practical question to test what you've just learned. Knowing how different surfaces handle thermal radiation, what color shirt should you wear on a hot, sunny day to stay as cool as possible? Just think about whether you want to absorb that solar radiation or reflect it. Thank you so much for joining me on this structured dive into the invisible yet highly impactful world of heat. Keep questioning the everyday world around you, and I will see you on the next explainer.